The information in this segment is really mainly for reference. I just want you to have the big picture of the historical reasons for why we adhere to the effect size guidelines that we currently do, and just to have an idea when a client later or someone at a conference later asks you what the value add of your study is or what the clinical significance of your findings are. Those kinds of questions are really effect size questions, and so hopefully this information will help you give informed answers to those kinds of inquiries. So who we have here is Jacob Cohen, and he had a very long, illustrious career as a psychologist, a statistician. He taught at NYU, I believe, for most of his career, and he literally wrote the book on multiple regression. Here in this slide, it's got a blue cover, and it reads more like an encyclopedia than anything else, great for reference to maybe have on your shelf. But many people have actually learned regression from this book. I used to have it as a required text, and I learned it as a graduate student from this book. But I'm just got to say that I'm very thankful for people such as Andy Field and Keith, who have gleaned the great concepts from Cohen's original work and have integrated it into, I think, a more consumable fashion for learning currently. So anyway, he did lots of work in the area of stats, but he also did work on effect sizes. And so in the 1960s, he took the Journal of Abnormal and Social Psychology. I think he just went through 1 or 2 years, I don't recall, but it was just that one journal, and he looked at all of the effect sizes in the studies, and he noted that the average effect size was about 0.4, so he assumed that that would be like a medium effect size, and then he said 0.2 was a small effect size, and then 0.6 would be a large. Later, he believed those to be overestimates, so he adjusted those rules of thumb, and you can read more about it in the notes under the slide. I don't want to get into it too much here. But all that to say that even Dr. Cohen himself admitted that this was a pretty subjective process that he went through. It wasn't scientifically rigorous necessarily, and so it's interesting to me that they're the guidelines that we still adhere to today. There are some critics who have talked about sticking with these, but for the most part, people just accept Cohen's original work on this. So that's what we still do today, and let me just switch gears and talk quickly about effect sizes in general now, and how they matter for power. So remember, if we have a large effect size in the population, we will probably have a large an increased likelihood of finding an effect in our study, even if we have a small sample. Conversely, if we have a smaller effect size going on in the population, then we will have to have more participants because our power is diminished. And so Guinness is kind of the one who has studied effect sizes a lot currently. He went through the literature on I don't remember which areas that he went through the literature, but he basically did a quick search across a wide range of studies that all looked at moderation. So an interaction analysis, and he found that most of those studies were underpowered. And that wasn't good. I mean, that's not a good thing, because we know that there are a lot of studies who don't get published, researchers who didn't have a high enough power and didn't find what they wanted to find, and so those don't even get into our journals, and so who knows how many of those there are. So Guinness basically said we need much more N to find moderation than we maybe thought we did, and he's written a lot about this, including some readings that you'll have later in the quarter, and so this is just something to keep in mind. Moderations take more N than I think mediation even does, depending. There's some exceptions, but moderation is going to require a lot of power to detect it. Okay, so there are two types of power analyses that we can do. The first one is a priori. That's before we collect our data for our study. And in that case, we want to know about how many participants we need in order to find the effect. And so remember that we need to have some idea of what the effect size is in the population, and the only way to really find that out is to look at studies that have been done in your area that are similar to your study on similar populations, and try to make a best estimate as to what that effect size is. Typically, I would say it's best to be conservative and just say small to medium effect size would be expected. I don't believe that it's probably wise to assume that you have a large effect size in the population unless you are doing a controlled experiment or you have very good reason to believe that's the case. But there's not a hard and fast science to looking through the literature to try to see what the effect size is in the population for the effect that you want to find. So one way that I've done, if I can have the resources to have a lot of participants, I will just assume the effect size is small and plan accordingly. So that's one way around it, going the conservative route. For the other way that you can do a power analysis is post hoc. So a reviewer, if you don't find what you were expecting to find, a reviewer, when you submit your study to a journal, they may ask you to do a post hoc analysis, which you would do with the number of participants that you had, and you'd put it into G-Power or some other calculator, and then you would figure out if you what kind of power you had. Did you have 0.8 power? And again, power is the probability of detecting a significant effect if it does really exist. So 80% power versus 85% power, or if your power was inadequate, it might be something closer to 40%. So post hoc is a way to do it as well. So that's the story behind power, and again, it's not an exact science, and knowing what's really happening in the population is not always easy because we don't have direct access to that, so we make our best guesses and do the best we can when planning our own research work.